Welcome back to another exam walkthrough. In this one, we're going to be going through a question from 2022, I think June. Okay, so this is question number 20. So let's look at this one. It's a very interesting question. So it says lead shot consists of small lead spheres. Originally, lead shot was made by dripping molten lead through a copper sieve and from the top of the tower. So from the top of the tower, they're going to drop molten lead. Molten means like kind of, it's not liquid exactly. It's kind of like a more viscous liquid. So it's kind of like an lead, but it's been melted basically, right? So it's molten, and the lead fell down, and as it fell down, it cooled, and before landing in water, it produced solid lead spheres. So it's going to fall down, okay. And then figure 1 shows a shot tower, so that's how it looks in real life, and then they've given you the diagram of that as well. So it's going to be very hot, it's going to fall down, it's going to transfer energy to the surroundings, and then it's going to become solid, and then it's going to fall into the cold water, okay. And then it says to avoid producing steam, they've kept the temperature below 100 degrees, so we don't want to produce steam, we don't want the cold water to turn into steam, so they're going to keep the temperature below 100 degrees Celsius. Okay, then they say a lead sphere falls to a distance of 41.5 meters. Show that the time taken is about 3 seconds for the sphere to fall through this distance. Assume the resistive forces are negligible, okay? So I'm just going to make use of the diagram, and I'm going to say that this distance is, okay, where did that go? Okay. So 41.5 meters. So this distance is 41.5 meters, and the lead is falling down in free fall. So the gravitational, or the acceleration due to gravity, is going to be 9.81. So we can just use the SUVAT. Okay, and remember from unit 1, if something is falling down, right, from the top, then its U is going to be 0. Right, so you have to remember that point, very important, that U will be 0. So I've taken the U to be 0. I've taken up as positive and down is negative, so the displacement is down, so it's going to be minus 41.5, and acceleration is minus 9.81 because it's going to be acting down, right? You can take it as positive, you'll get the same answer. So the equation I'm going to be using is S is equals to ut plus half at squared. Since u is 0, so I'm going to cancel this out. So S is equals to half at squared. So when I manipulate it further, I'm going to get t is equals to square root 2s divided by a. And I'm going to plug in the values. The minus signs have cancelled out because this is minus and this is minus, so the minus signs cancels out. So the minus sign is cancelled out, and I'm going to get the answer as 2.9087 seconds. In the next question, it says the lead sphere has a radius of 1.2 millimeters. As it falls, it cools from 615 Kelvin to 370 Kelvin, and the molten lead solidifies at 601 Kelvin. Calculate the mean rate at which energy is transferred from the lead sphere to the surroundings. You should assume that the specific heat capacities of the liquid and solid lead are same. Okay, and the mean rate here just simply means we have to calculate the power. So they're saying us to calculate the power. That's basically what they're asking. Now the energy that is released when the lead changes states from molten to solid, and to change from molten to solid, it's going to be m, the mass, times L, okay? And then the energy that is required to increase the temperature is going to be mc, change in the temperature. So first I'm going to find mass, which I know mass is equals to density times volume. And density is 1.13 times 10 to the raised power of 4. And then volume I know is 4 by 3 pi, and then r cubed. So r is in millimeters. I'm going to do 1.2 times 10 to the raised power of minus 3 to change it to meters, and then cube. And that's going to give me the mass. And that's going to give me 8.179 times 10 to the raised power of minus 5 kg. And when I plug it into this equation, where I'm going to be calculating the energy required, the energy released, so that the molten lead becomes solid lead, and I'm going to get the value from this equation as 2.02 joules. Now the energy required to increase the temperature should have the same mass. So I'm going to plug in the mass value here. Let's put the mass value right over there. And then what I'm going to do is I'm going to plug in the specific heat capacity of lead. Plug in the specific heat capacity of lead, which is 130. And then I'm going to get my change in temperature from up there, which is just going to be me subtracting both of the values. So I'm going to do 615 Kelvin minus 370 Kelvin. I'm going to get 2.604 joules. So I'm going to add both the values and I'm going to get 2.02 plus 2.604. And the amount of time it takes for the lead to go from the top to the bottom is 2.9087 seconds, right? So this is the time taken for lead to go from here to here and for all of this stuff to happen. So I'm just going to divide it by 2.9087 seconds and joules. So it will be joule per second, which is basically power. That's going to give me 1.59 watts. So in part B, it says a teacher demonstrates a mechanical method to determine the specific heat capacity of lead. Some lead shot at a room temperature is placed in the perspex tube, and then it says the teacher turns the tube upside down and the lead shot falls through a distance t. The teacher repeats this n times and measures the final temperature of the lead shot. So the teacher will kind of flip this up and down, right? And she'll do it a number of times, and then she'll note down the final temperature, and then she'll find the change in temperature. The teacher uses the values of d, n, and change in the temperature to determine the value of specific heat capacity of lead. Now, before we further answer this question, let me show you what's actually happening. So you're going to have the lead shots in here, and the lead shots are right over here. And when you flip this tube, so you flip it, the lead shots will fall down and they will gain energy. And then once they're here, you'll flip it again, and then you'll keep flipping and doing this, and you will note down the temperature. So initially your temperature will be theta I, and then after flipping it for a number of times, let's say at least 50 times, you note down the final temperature, and then you find the change in temperature. Right, so you're going to get the change in temperature, and let's say you have flipped this thing around 50 times, right? And then you're going to find the mass of the lead shot. Now I'll show you why the mass isn't really that important, but let's just assume right now that we need all of these things, okay? And then we have this distance d. I've written it as h, but let's say distance d, okay? I hope that makes sense. So all of these things we're going to be using, and then we also need we need to find the value of c, right? That's what we're trying to find. Okay, very, very important thing, right? As soon as I flip this thing, the balls fall from the top to the bottom. So what's going to be happening is that the GPE will be converting to KE, right? When things go down, the GPE converts to KE, and the KE will be converting into the internal energy of the balls, okay? And this gain in the internal energy is actually going to result in the increase in the temperature, because when they gain the internal energy, their temperature rises, because when their internal energy increases, your temperature should also increase. So that's what's causing the increase in temperatures, because you keep moving it around. So you're going to keep providing GPE, and that GPE will convert to KE, and that KE will convert to internal energy, and this is going to keep happening until there is a significant enough temperature increase. That's why we do it a bunch of times, because the temperature increase will be very small. So we have to make sure it's big enough for us to subtract the values and even see it on the thermometer. Okay, so we're going to do all of that. Now, basically I can say that the GPE that is gained is equals to the GPE that's lost and the KE that's gained when they fall down. So I'm going to write mgh is equals to half mv square, and that half mv square is equals to mc change in temperature, right? So the lost GPE that's lost is converted into the KE that's gained, and the Ke is then lost or transferred. The Ke energy is transferred into the energy that is used to increase the temperature. Okay, so I can basically say that this energy goes into this, right? In short, so I can say mgh is equals to mc, change in temperature, and I can cancel the m out. That's why I was saying we don't really need the m value of the lead, so we don't need the mass of lead shot. So I'm going to say gd, so this distance was d, is equals to c, change in temperature. And I've done this experiment 50 times or n number of times, so I'm going to write n here, right? N as n times the distance, right? Because the balls have covered, if they move 50 times, they've covered this distance 50 times, right? So I'm going to put n times d, okay? So my c will be equals to ngd divided by change in the temperature. Okay? So that's going to be my value of the specific heat capacity. Okay, here is basically the entire thing that I've done now. Okay, and it's in a really proper working. So here they have taken mgh and they've multiplied it by 100 because they flipped this thing 100 times. So they flipped it 100 times, and the ball moved a distance h 100 times. And so they put 100 there, and the m's cancel out, and then you get c is equals to 100 gh, and the change in the temperature. Okay, this is a very important formula. So they're asking you, explain why the mass of the lead shot should not affect the value of change in theta. So you can use lead shot of any value, like which has any mass. Okay, it can have 5 kg, 10 kg, doesn't matter what the mass is, because the mgh is equals to mc, change in temperature. Okay, or the gravitational potential energy is transferred into, or the change in gravitational potential energy is going to be equals to the change in internal energy of the lead shot. Okay, and this actually causes the temperature change. So the m's will cancel out. So you can say that c is independent of the mass of lead shot. Okay, so it required a little bit of context. This was a bit of a tricky question. Okay, and now we're going to go at the last part, which is assess whether this method would produce an accurate value of c. So possible reasons why this method wouldn't give you an accurate value for c will be some energy can be transferred to the surroundings, and that this won't be an accurate method because it's possible for the value of T to be too small, right? So if it's too small, then your thermometer, even if you have a digital one, may not be able to be sensitive enough to detect that change, okay? So yeah, so that's the answer to this. I'm going to be showing you the mark scheme and the examiner report. Here is the mark scheme, and we have the examiner report on the other side.